Turns out the break-even rate is 5.14%. So under expectations hypothesis, the 2-year rate should be 5.14. Of course, you could repeat all of these exercises given the short-term rates and expectations about the future, and we take the forward rates to be the expectations. It kind of determines the yield curve. The trouble is the empirical evidence does not support that too much. So if I did a study and calculating forward rates is not much of a problem. We've done it before. We did, templates and stuff. Given the spot rates, we can calculate the forward rates. I calculate that 1 year from now, 1 year forward rate is 3.5%. Then I wait for 1 year. I look at what happened to the 1 year rate 1 year from now. 4%, 2%, one hand. If you've done this study historically, you find out that there is a significant gap between the future rates, future short-term rates predicted by the forward rates, or what we call the forward curve, and the actual rates. So empirical evidence is not that supportive. It's a nice little teaching tool, but you cannot actually plan based on that. There are two more kind of theories. One of them is called the liquidity preference. Investors and borrowers tend to want to be in environments where these borrowing and lending tools are liquid. So, which means the more liquid they are, there is actually a premium, or the interest rates tend to be a little bit lower. The less liquid they are, they tend to be a little bit higher. In fact, I'm going to show you a nice little example of that's the case. Treasury has some, or Federal Reserve has a website. In fact, this is called Release H15. It kind of gives you a summary measures of indicative measures of the yield curve. Currently, the 30, 20 years or 10-year yields are 429. This is as of a week ago. This is a weekly release. So I think tomorrow we should have to get the new release. But there's a little jump to 20 years to 461. Why that is the case, we'll talk about that, but for now, don't worry about it. But oddly enough, 30-year rate is lower. In fact, this gap is actually right now smaller than it used to be. Sometimes there's a very significant gap between the 20-year rate and the 30-year rate. That doesn't make sense on its own. I mean, forget about anything else. Let's take the expectations theory seriously for now. According to that, I should be expecting 10-year rates to be a little bit higher between year 10 and 20 compared to the between years 20 and 30. If we take that theory literally. Why? Because 20-year rates are higher. The only way expectations theory would tell me that 30-year rates are going to be lower, I should be expecting 10-year rates to be lower during the last 10 years instead of the second 10 years. Does that make sense to anybody? I mean, I'm a goddamn surgeon with statistics. If I wanted to, I could even use all these machine learning models and be a great forecaster. I have done that as a job way back when. If anybody asked me to produce a forecast of economic activity, financial activity, and make a serious distinction between year 10 and 20 and years 20 and 30, I would have told them go home in a non-polite way. Okay, because it's impossible, even independent of all the technological, geopolitical stuff that's going to happen. It's called the second law of thermodynamics. Entropy always increases. Entropy is the fancy word for disorder. Okay? Given the information I have right now, quality of forecast I can make, even with great statistical skills, is always lower in the longer term compared to shorter term. So as far as forecasting is concerned, there's no difference between 20 years and 30 years. But why is there that difference? You think that 3 basis points is just a small number. If you know anything about financial engineering, and I'm hoping you'll find out if that's something you want to work on, uh, you can make crap loads of money with that 3 year differential, 3 basis points differential. In fact, long term capital management kind of made, uh, come on, this was a hedge fund that went down back in 1998 after Russia went down. I think I did talk to you guys about the difference between the new bond and the old bond. Every 6 months, U.S. Treasury issues a 30-year bond issue. And when the new bond is issued, the 29.5-year-old bond is called an old bond. For all practical purposes, there is no difference between the two as far as inflation risk, as far as any risk that the U.S. government uh, may not be able to pay it back. Trust me, if they're going to default in 30 years, more than likely they're going to default in 29 and a half years. If there's going to be high inflation 30 years from now, do you really think that 29.5 year inflation is going to be any lower? No. Even with deterministic systems, things can vary a lot. Do you guys know about the so-called chaotic systems? These are completely deterministic systems. You can have two things start very close to each other, but over time they can have a completely different path. In mathematics, we also call these fractals. I'll give you an example. This is a completely deterministic system. I mean, pictures are beautiful, but uh, I used to do a lot of coding to generate these pictures way back when I didn't want to write the literature review for my PhD dissertation. Okay, Julia sets. These are mathematical sets that are named after a French mathematician named Gaston Julia. Okay, come on, give me a nice little picture. Okay, these are the so-called boundaries of Mandelbrot set. Let me put this boundary. You know how that picture is generated? Uh, think of a very simple polynomial. X cubed equals 1. But in this case, X can be a complex number. There are numerical methods. I mean, we know how to solve that algebraically, but there are numerical methods where you start with an initial guess, then you apply so-called Newton's algorithm. Every time it supposedly gets you closer. Okay. and it finds the solution. The way you get that picture, this has three routes. You start from a certain guess, you apply the algorithm. If it converges to the first route, you color it blue, whatever your color is. If it converges to the second route, you color it green. Converges to the third route, you color it what you want to call red. Sometimes it explodes because Newton's algorithm is not a stable method, at least for that. You color it black. That's what that interior is. Oddly enough, if you actually can and do zoom on the boundary of that picture, it keeps repeating the same pattern. So you can have two guesses that are arbitrarily close to each other, but they go to different places. So even with deterministic systems where you actually know where things are going,